Assalamualaikum and a very good day to all the panels. I hope you are doing fine during these trying times. My name is Muhammad Irfan Muqri. I am under the supervision of Dr. AHMAD KHUSHAIRY and co-supervision of Encik KHAIRUL IMRAN. Today, I would like to present on a study on safety driving behavior by using an open source software. This presentation will include the introduction, objective of study, scope of study, methodology, result and discussion, and conclusion. Ministry of Transport Malaysia reports that road accidents recorded in Malaysia has been increasing from 2010 to 2019. However, reported road accident casualties has been steadily decreasing from 7,152 to 6,167 in 2019. Fatalities caused by road accidents in Japan in 2019 is 3,215. If we take the population of Malaysia and Japan into consideration, the number of cases in Malaysia is still higher than Japan. So, what is the causes of road accidents? One of the main causes of road accidents is the behavior of the driver, more specifically, driver's distraction. It is defined as acts that occurs inside or outside the vehicle that impairs a driver's ability to process information required to properly operate a vehicle. So the problem statement is that there is not enough data regarding driver distraction in Malaysia. The primary available research is based on a survey of driver behavior while driving. Next is manually gathered data on driver behavior analysis is tiring and a lot of work. It requires many manpower and resources. The objective of this study is to gather data on drivers' behavior, to develop a program to detect drivers' behavior from outside the vehicle, and to discern the type of driver behavior which is normal driving or distracted driving. First, the video recorded is only for cars, vans and lorry. Motorcycles and emergency vehicles are excluded. Next, creating a detection program using OpenCV and Python as the language to detect the driver behavior. Lastly, creating a HAR cascade classifier to train the program. The software used in this study is OpenCV along with Python as the programming language. The computer vision program will then exploit the HAR cascade classifier to detect the driver's behavior when driving. OpenCV is an open source computer vision and machine learning software library. It includes more than 2,500 optimized algorithms in the library. It can also be used to identify objects, detect and recognize faces, categorize human behavior in videos, and track moving objects. Next is coding. PyCharm is used as the IDE to develop the program. It supports Python and OpenCV, and it has a community version, which is the free version, with all the tools that needed in this study. Next is the track bar. The track bar is added into the code to increase the efficiency of the detection program. It is used to manipulate the scale value, nearest neighbor value, minimum area value, and brightness. So, what is nearest neighbor? Nearest neighbor is one of the most basic supervised learning classification algorithms. Its functions is to find the test data's closest match in the feature space. This is the example for how the program will display if it detects the driver behavior. Left one is for normal driving, the right one is for distracted driving. Next is how the video is recorded. The video is recorded using a smartphone camera. It is placed on a tripod for stabilized recording. It is placed on a pedestrian overpass for it to record from an upper view, which can give a clear view of the driver inside the car. The location of the recording is on a pedestrian overpass in section 21 Shah Alam. Cascade classifier. The program will use HAR cascade classifier to train. A set of positive images and a set of negative images are required for cascade classifier training. Pattern recognition uses qualities taken from images called HAR-like features. Their name comes from their resemblance to HAR wavelets. To train the cascade classifier, the Cascade Trainer GUI is used. The trainer will use a graphical interface to set the parameters and make it easy to use OpenCV tools for training and testing classifiers. It is a program that can be used to train, test, and improve the cascade classifier models. These are the type of driver behavior that will be measured in this study. These terminology are taken from the National Highway Traffic Safety Administration. First is normal driving. The driver does not involve or engage in any distraction activity or secondary task while driving. Next is the use of mobile phone. The driver is observed engaging with his or her mobile phone while driving, whether in a situation of holding it for texting or hold the mobile phone close to their ears. And lastly is eating or drinking. The driver is holding, eating or drinking some form of food or beverages. The use of mobile phone and eating or drinking are both categorized into distracted driving. Two datasets have been used to train the HAR cascade. Dataset 1 is for normal driving and dataset 2 is for distracted driving. Each dataset contains two sets of folders filled with positive and negative images. Left image shows example of positive images for normal driving and right image is for distracted driving. For more accurate detection, the negative image must be more than the positive image. In creating the HAR cascade classifiers, a set of positive and negative images folders are created. Positive image contains an object that must be detected, whereas a negative image does not contain the object to be detected. In this case, the positive images are the driver behavior, while the negative images include cars, trees, motorcycles, and the road.
This video will show how to create the HAR cascade classifier using the GUI trainer. First, create a cascade folder containing the positive images and negative images. Then import the folder into the trainer. Then set the number of negative images. And then start the trainer. It can also adjust the amount of stages to create the HAR cascade, and usually it is set to default. After the process is done, a cascade file is created along with a cascade file in XML. This video will show the coding for the program. This is the coding for the normal driving detection. The normal driver detector is shown in a green box. Motorcycles and roads are exempted from being detected. Glare on windshield is also exempted. Next is the code for distracted driving detection. It has similar code but with different HAR cascade files. The track bar setting is also different. Distracted driving behavior will show a red box.
To test the program, 3 videos containing both normal driving and distracted driving is used to test if the program can detect the driver behavior or not. For video 1, the length is 1 minute, video 2 is 2 minutes and 40 seconds, and video 3 is 1 minute. The program is trained, validated, and tested with the two datasets. Each of the datasets have a specific track bar setting. To get more accurate result, the track bar must be fine-tuned and consistent when testing the program. One background video is also used, which only contains a road with no vehicle passing. The background video is used for track bar setting so that it will consistently detect the driver inside the car and not the road. The image shows how the program will indicate what type of driver behavior is being detected. The track bar shows the setting for normal driving. With the scale value being lowered, more computational power will be used and making the detection program more sensitive. Other use for this setting is for slowing down the video so that it can properly detect the driver inside the car when the car passes through. The track bar shows the track bar setting for distracted driving detection. The scale value and nearest neighbor value are decreased, the computational power will increase, and the closest match to the data will also increase. The image shows how the program indicates when distracted driving is detected. The efficiency for distracted driving is lower, with the possibility of being the data for distracted driving is much lower compared to normal driving. Finally, in the background video, the number of true positive and false positive examples are insufficient to draw any conclusion. The table shows the result of the sample video for detection testing for normal driving. Video 1 has 20 total vehicle pass with 2 successful detection. Video 2 shows 50 total vehicle pass with 19 successful detection. Video 3 shows 19 total vehicle pass with 7 successful detection. The next table shows the result of the sample video for the detection testing for distracted driving. Video 1 has 0 successful detection, the same result for video 2, and 3 successful detection in video 3. The reason the results for distracted driving are low is because there are not many drivers with distracted driving in the video. When observe the video and count manually, the 3 successful detection is out of 4 total distracted drivers when not counting the tinted vehicle. 1 out of 4 is not successful to be detected. Next is discussion. Not all vehicles can the drivers be detected. This is because of poor visibility on the vehicle's windshield. With new regulation from JPJ Malaysia, light transparency tint can now be up to 70% transparency. Because of this, more cars can be seen with tinted windshield, making it almost impossible to see the driver. Aside from that, weather and recording timing is also a factor for the visibility issues. Glare from the sunlight and shadows from nearby buildings and trees can affect the visibility to see the driver properly. Because of this, several positive data that should be included in positive images for training the HAR cascade classifier are transferred into the negative images. Next is insufficient data for distracted driving. The reason why the setting for track bar in distracted driving is different to normal driving is because of insufficient data. In the 2-hour video recording, only 100 images can be processed as the positive images for distracted driving as opposed to 400 images for normal driving. This is because many of the drivers tend to behave well when seeing the observer on the pedestrian overpass. Some drivers have anxiety when seeing speed trap cameras while driving. Therefore, it is more difficult to see distracted driving than normal driving during the recording phase of this study. Next is false detection. These are examples of false detection during the testing. Any false detection can be attributed to one of two issues: inadequate training examples or many training stages. The general shape of cascade classifier is like that of a degradation tree. To attain a high detection rate, a positive result from stage 1 is altered and resulted in stage 2. The process repeats until it reaches the set stages. After that, it stops. So, the more stages used, the more degradation will occur to the training examples. Finally, the limitation of this study is that it is difficult to determine the classification of the type of driver behavior. This is because the images to be used as sample data are not clear enough, and some behavior, such as texting, cannot be seen when the driver hit their hand under the steering wheel. During the recording period, the weather can suddenly change, making it not suitable to record any data. It also challenging to decide which lane to record the driver behavior, as the camera used cannot focus on the 3 lanes simultaneously. It is decided that the middle lane will be recorded by doing counting of vehicle passing beforehand. In conclusion, the usage of OpenCV as a tool to make an observation to study the behavior of drivers in Malaysia can be achieved. Given enough budget and a team, further improvement on the existing codes can be done to improve the efficiency of the detection program. For this research, the objective to develop a driver behavior detection program from outside is achieved. Thank you for your time to listen to this presentation. If anyone has a question, you can contact me at the following details. Thank you. Assalamualaikum and have a good day.